From the moment our ancestors first looked up at the night sky, a profound question ignited within the human spirit. Are we alone? This question, simple yet deeply resonant, has echoed through millennia, driving us to explore, to understand, and to dream of other worlds and the life they might hold. The vastness of space, with its twinkling stars and distant galaxies, has beckoned us with the promise of discovery and the allure of the unknown. The contributions of early astronomers, often working in isolation or with limited resources, were nothing short of extraordinary. From the ancient Babylonians, who developed sophisticated methods for predicting eclipses, to the Greek astronomer Ptolemy, whose geocentric model of the universe dominated scientific thought for over a millennium, these pioneers paved the way for future generations of astronomers. Isaac Newton, an English physicist and mathematician, revolutionized our understanding of gravity and its role in the cosmos. His law of universal gravitation, published in 1687, stated that every object in the universe attracts every other object, with a force proportional to their masses and inversely proportional to the square of the distance between their centers. This elegant equation explained why planets orbit the sun in elliptical paths and provided a unified framework for understanding the motions of celestial bodies. Newton's work marked a turning point in the history of science, ushering in an era of unprecedented progress in physics, astronomy, and mathematics. The development of calculus, a powerful mathematical tool invented independently by Newton and Gottfried Wilhelm Leibniz, provided scientists with new ways to describe and analyze motion, change, and other fundamental concepts. With the advent of space exploration in the mid-20th century, our ability to study the universe took another giant leap forward. Telescopes placed in orbit above Earth's atmosphere, such as the Hubble Space Telescope, provided unprecedented views of the cosmos, free from the distortions caused by Earth's atmosphere. Space probes have visited all the planets in our solar system, beaming back stunning images and a wealth of data that have revolutionized our understanding of these celestial bodies. Our exploration of the cosmos has revealed a universe far vaster and more diverse than our ancestors could have ever imagined. We now know that our solar system is just one of billions of star systems in the Milky Way galaxy, which itself is just one of billions of galaxies in the observable universe. This cosmic perspective has profoundly altered our view of ourselves and our place in the grand scheme of things. In our quest to find life beyond Earth, we often find ourselves returning to a fundamental concept known as the habitable zone, sometimes referred to as the Goldilocks zone. This term, inspired by the classic fairy tale, describes the region around a star where conditions are just right, not too hot, not too cold, for liquid water to exist on the surface of a planet. Water, as we understand it, is the lifeblood of our planet and a crucial ingredient for life as we know it. Imagine a star as a campfire on a chilly night. Get too close and you'll be scorched by the intense heat. Venture too far away and the cold will seep into your bones. The habitable zone represents that sweet spot, the comfortable distance from the campfire where you can bask in its warmth without being consumed by the flames. Similarly, a planet within the habitable zone of its star receives just the right amount of energy to maintain liquid water on its surface. Determining the precise boundaries of the habitable zone is a complex task, as it involves considering a multitude of factors beyond just the distance between a planet and its star. A planet's atmosphere, for instance, plays a crucial role in regulating its surface temperature. Greenhouse gases like carbon dioxide trap heat, warming the planet's surface, while clouds can reflect sunlight, cooling it down. The presence or absence of a magnetic field is another critical factor. Earth's magnetic field acts as a shield, protecting us from harmful radiation from the sun. Without a magnetic field, a planet's atmosphere can be stripped away by the solar wind, leaving its surface exposed to the harsh radiation of space. While our search for life beyond Earth initially focused on our own solar system, the discovery of exoplanets, planets orbiting other stars, has opened up a vast new frontier in the search for extraterrestrial life. Since the first exoplanet was discovered in 1992, thousands more have been detected, revealing a staggering diversity of worlds beyond our own. Among these exoplanets, astronomers have identified several that reside within the habitable zones of their host stars, raising the tantalizing possibility that these distant worlds could harbor liquid water and, potentially, life. These Goldilocks planets have become prime targets in the search for extraterrestrial life, captivating the imaginations of scientists and the public alike. The presence of liquid water, while considered a key requirement for life, is not the only factor that determines a planet's habitability. Life, as we understand it, requires a complex interplay of chemical elements and energy sources to emerge and thrive. Carbon, with its unique ability to form long chains and complex molecules, is considered the backbone of life on Earth. Other essential elements include hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These elements, collectively known as CHNOPs, are the building blocks of proteins, nucleic acids, lipids, and other essential biomolecules. The concept of the habitable zone, while a valuable tool in our search for life beyond Earth, should not be viewed as a rigid or limiting factor. Life, as we know it, is remarkably adaptable, thriving in a wide range of environments on Earth that were once considered uninhabitable. Extremophiles, organisms that thrive in extreme conditions, such as high temperatures, extreme pressures, or highly acidic environments, demonstrate the incredible resilience of life. These organisms have expanded our understanding of the limits of life and raised the possibility that life could exist in environments vastly different from our own. While our search for life beyond Earth often focuses on distant stars and exoplanets, our own solar system harbors a treasure trove of celestial wonders that have captivated scientists and fueled our imaginations for centuries. Moons. These celestial siblings, orbiting planets both near and far, exhibit a remarkable diversity in size, composition, and potential for harboring life. From the volcanic plains of Io to the icy plains of Europa, the moons of our solar system offer a glimpse into the incredible variety of worlds that exist within our cosmic backyard. For centuries, astronomers viewed moons as mere points of light, their true nature shrouded in mystery. However, with the advent of space exploration in the mid-20th century, our understanding of these celestial bodies underwent a profound transformation. Space probes, dispatched to explore the outer reaches of our solar system, beamed back stunning images and a wealth of data that revealed moons to be far more complex and intriguing than we had ever imagined. Orbiting Jupiter, the largest planet in our solar system, lies Europa, a celestial enigma that has captivated scientists and dreamers alike since its discovery by Galileo Galilei in 1610. Covered in a shimmering, icy shell, Europa may appear at first glance to be a frigid and desolate world. However, beneath its icy exterior lies a hidden ocean, a vast global expanse of water that is thought to contain more water than all the oceans on Earth combined. The presence of this subsurface ocean, confirmed by observations from spacecraft such as Galileo and Hubble, has catapulted Europa to the forefront of the search for extraterrestrial life. Scientists believe that Europa's ocean, shielded from the harsh radiation of space by its icy shell, could potentially harbor the necessary conditions for life to exist. Enceladus, a small icy moon orbiting Saturn, might seem like an unlikely candidate for harboring life. However, this tiny moon has surprised scientists with its unexpected activity and tantalizing hints of a potentially habitable environment beneath its icy surface. Discovered in 1789 by William Herschel, Enceladus remained largely enigmatic until the Voyager spacecraft flew past it in the early 1980s, revealing a surprisingly bright and reflective surface. In 2005, the Cassini spacecraft made a groundbreaking discovery that revolutionized our understanding of Enceladus' gigantic plumes of water vapor erupting from the moon's south polar region, spewing icy particles and organic molecules hundreds of kilometers into space. These plumes, originating from a region dubbed the Tiger Stripes due to their distinctive surface features, provided undeniable evidence of a vast subsurface ocean lurking beneath Enceladus's icy shell. Titan, Saturn's largest moon, is a world of stark contrasts and enigmatic beauty. Shrouded in a thick, hazy atmosphere, Titan is the only moon in our solar system known to have a substantial atmosphere, one that is denser than Earth's and composed primarily of nitrogen, with traces of methane and other organic molecules. This dense atmosphere creates a unique environment on Titan, one that is both familiar and alien. Discovered in 1655 by Christian Huygens, Titan remained shrouded in mystery for centuries, until the Voyager spacecraft provided the first glimpses of its surface in the early 1980s. However, it was the Cassini-Huygens mission, which arrived at Saturn in 2004, that truly unveiled the wonders of this enigmatic world. The Huygens probe, carried by Cassini, descended through Titan's atmosphere, making a historic landing on its surface in 2005. Europa, Enceladus, and Titan are just a few examples of the many moons in our solar system that have captivated scientists with their potential for harboring life. As we venture farther out from the sun, beyond the frost line where temperatures plummet, we encounter a realm of icy giants and their enigmatic moons, some of which may also harbor hidden oceans beneath their frozen surfaces. Ganymede, the largest moon in our solar system and a moon of Jupiter, is another intriguing candidate in the search for extraterrestrial life. Larger than the planet Mercury, Ganymede possesses a complex geology, with evidence of past tectonic activity and a possible subsurface ocean sandwiched between layers of ice. Our exploration of the cosmos extends beyond searching for life in the traditional sense of seeking out water, organic molecules, and habitable environments. It also encompasses a profound endeavor that has captivated humanity for decades, listening for signals from intelligent civilizations beyond Earth. This quest, fueled by both scientific curiosity and a deep-seated desire to know whether we are alone in the universe, has led to the development of a dedicated field of research known as the Search for Extraterrestrial Intelligence, or SETI. The premise of SETI is both simple and audacious. If intelligent civilizations exist elsewhere in the universe, they might be transmitting signals into space, either intentionally or unintentionally, that we could detect with sufficiently sensitive instruments. These signals could take many forms, from radio waves to laser pulses to other forms of electromagnetic radiation that could traverse the vast distances between stars. The search for extraterrestrial signals is intimately linked to the field of radio astronomy, a branch of astronomy that studies celestial objects by observing the radio waves they emit. Radio waves, a type of electromagnetic radiation with much longer wavelengths than visible light, can penetrate the vast clouds of gas and dust that obscure our view of the universe at optical wavelengths. Radio astronomy emerged in the 1930s with the accidental discovery of radio waves from the center of our Milky Way galaxy. Since then, radio telescopes have become increasingly sophisticated, allowing astronomers to probe the universe in unprecedented detail. These telescopes, often massive structures with large dishes or arrays of antennas, collect faint radio waves from space and convert them into signals that can be analyzed to reveal information about the temperature, composition, and motion of celestial objects. The modern era of SETI began in earnest in 1959 with a seminal paper by physicists Giuseppe Cocconi and Philip Morrison, who proposed that radio waves would be an efficient means for interstellar communication. They suggested that a frequency of 1,420 MHz, known as the hydrogen line, would be a logical choice for extraterrestrial civilizations to transmit signals, as it corresponds to the natural emission frequency of neutral hydrogen, the most abundant element in the universe. Inspired by Cocconi and Morrison's paper, astronomer Frank Drake conducted the first modern SETI experiment in 1960, known as Project Ozma. Using the 85-foot Howard E. Tatel radio telescope at the National Radio Astronomy Observatory in Green Bank, West Virginia, Drake pointed the telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, listening for any artificial radio signals. Although Project Ozma did not detect any extraterrestrial transmissions, it marked the beginning of a sustained scientific effort to search for evidence of other technological civilizations. The detection of a potential extraterrestrial signal would be a momentous occasion, but it would also mark the beginning of a new set of challenges, deciphering the signal and understanding its meaning. If an extraterrestrial civilization were to send us a message, it is highly unlikely that they would be using English, Swahili, or any other human language. Instead, we would need to develop methods for decoding the signal based on its underlying structure and patterns. One approach to deciphering an extraterrestrial signal would be to look for mathematical or physical constants that are universal, such as the speed of light, the gravitational constant, or the mass of an electron. If an extraterrestrial civilization were attempting to communicate with us, they might choose to encode these constants in their signal as a way of establishing a common language. The search for extraterrestrial intelligence is a testament to humanity's insatiable curiosity and our deep-seated desire to understand our place in the cosmos. While we have yet to detect a confirmed signal from another civilization, the ongoing efforts of SETI researchers continue to push the boundaries of our technological capabilities and expand our understanding of the universe. The lack of a definitive detection thus far does not necessarily imply that we are alone in the universe. The vast distances between stars, the limitations of our technology, and the possibility that other civilizations may be using communication methods that we have not yet discovered all contribute to the challenge of SETI. Our journey to understand life beyond Earth, to unravel the mysteries of the cosmos, and to search for signs of other intelligent civilizations is far from over. Driven by an unquenchable thirst for knowledge, we stand on the cusp of a new era in space exploration, one that promises to be even more transformative. The next giant leap will be fueled by advances in material science, propulsion systems, and AI. These advancements will enable us to build more powerful telescopes, send probes to distant star systems, and establish a sustained human presence in space. Our ability to observe the universe has always been limited by the power of our telescopes. Just as Galileo's rudimentary telescope revolutionized our understanding of the cosmos centuries ago, so too will the next generation of telescopes unlock even greater secrets, revealing the universe in unprecedented detail and pushing the boundaries of our knowledge. One of the most anticipated telescopes of the future is the James Webb Space Telescope, the successor to the Hubble Space Telescope. Launched in December 2021, JWST is the largest and most powerful space telescope ever built, with a primary mirror 6.5 meters in diameter, compared to Hubble's 2.4-meter mirror. This massive mirror, along with JWST's advanced infrared instruments, will allow it to peer deeper into space and time than ever before, observing the first galaxies that formed after the Big Bang, studying the atmospheres of exoplanets for signs of life, and unraveling other cosmic mysteries. While telescopes provide us with a window into the distant universe, the ultimate goal of space exploration is to venture beyond our solar system and explore other star systems firsthand. This ambitious goal, once relegated to the realm of science fiction, is now within the realm of possibility, thanks to advances in propulsion systems, spacecraft design, and our understanding of interstellar space. One of the most promising concepts for interstellar travel is the light sail, a spacecraft propelled by the pressure of sunlight or laser beams. Just as a sailboat uses the wind to move across the water, a light sail uses the momentum of photons, particles of light, to accelerate through space. While the force exerted by photons is incredibly small, it is continuous, allowing a light sail to gradually accelerate to a significant fraction of the speed of light over time. Our exploration of space is not limited to robotic probes and telescopes. As we venture further into the cosmos, we will need to establish a sustained human presence in space, creating self-sufficient habitats where humans can live, work, and thrive for extended periods. Space habitats, often envisioned as giant rotating structures, could provide artificial gravity, protection from radiation, and a controlled environment where humans could live comfortably for long durations. These habitats could be built using materials harvested from the moon, asteroids, or other celestial bodies, reducing the need to transport materials from Earth. Our exploration of the cosmos is more than just a scientific endeavor. It is a profound reflection of the human spirit, our innate curiosity, our desire to understand our place in the universe, and our yearning to connect with something larger than ourselves. The search for life beyond Earth, the quest to unravel the mysteries of the cosmos, and the dream of one day traveling to the stars are all expressions of this fundamental human drive. As we stand on the verge of a new era in space exploration, it is important to remember that the journey itself is just as important as the destination. The challenges we face, the discoveries we make, and the knowledge we gain along the way all contribute to our understanding of the universe and our place within it. As we conclude our exploration of life beyond Earth, we reflect on the vastness of the cosmos and the profound implications for humanity. The search for extraterrestrial life is a search for ourselves. It is a journey of self-discovery to understand our place in the universe. Are we alone, or are there other beings out there? The answer will shape our understanding of ourselves. The discovery of even the simplest life forms on another planet would be a profound revelation. It would demonstrate that life is not unique to Earth. The spark of life can ignite in unexpected places. Such a discovery would force us to reevaluate our assumptions. As we gaze up at the night sky, our eyes drawn to the twinkling stars and the ethereal glow of distant galaxies, we are filled with a sense of awe and wonder. The universe, in its vastness and complexity, continues to amaze and inspire us, challenging our assumptions and expanding our horizons. The search for life beyond Earth is but one facet of this grand exploration, one thread in the intricate tapestry of cosmic discovery. Every new discovery, from the detection of a distant exoplanet to the unraveling of the mysteries of dark matter and dark energy, deepens our understanding of the universe and our place within it. We are reminded that we are part of something much larger than ourselves, a cosmic web of interconnectedness that spans billions of light years and encompasses countless wonders yet to be revealed. The quest to understand life beyond Earth, to explore the cosmos, and to search for signs of other intelligent civilizations is more than just a scientific endeavor. It is a legacy we leave for future generations. It is a testament to our curiosity, our ingenuity, and our enduring desire to unravel the mysteries of the universe. The knowledge we gain, the technologies we develop, and the inspiration we spark will continue to shape the course of human history long after we are gone. Imagine a future where humans have established a sustained presence in space, living and working not only on Earth, but also in orbiting cities, lunar outposts, and even settlements on Mars. Imagine a future where we have developed the technology to travel to other star systems, to explore distant exoplanets, and perhaps even to make contact with other intelligent civilizations. This is the future we are striving to create, a future where the boundaries of human potential are limitless.